can I start?
Yes.
Yes, please.
Okay, great. Yeah, thank you. So yeah, I want to continue with hierarchies. So yesterday we derived the moment hierarchy for polynomial optimization problems, and which is dual to the central squares hierarchy that we looked at in the first lecture. And then at the end, we specialized this moment hierarchy to, well, first to 0-1 polynomial optimization problems, and then to the independent set problem. So today I want to go from this to hierarchies for point configuration problems on the sphere, for instance. So yeah, and in particular, I want to consider packing problems. So one packing problem is the spherical code problem. So here we are given a dimension n and an angle theta. And the question is, what is the largest set in the unit sphere such that the dot product between any two distinct points in the code is at most cosine theta. And why do I call this a packing problem? Well, you can imagine that each point in the spherical code is the center of a spherical cap, and that way you're packing spherical cap. So this is really the compact analog of the sphere packing problem. Yeah, so why do we want to consider hierarchies for the independent set problem? Well, we can view these packing problems as independent set problems in certain graphs. So for instance, for the spherical code problem, you can consider the graph with vertex at the unit sphere, where two distinct vertices x and y are adjacent if the dot product is strictly greater than cosine theta. Yeah, so and now we want to set up this theory not just for this graph, but for sort of general graphs that appear if you study a packing problem. So here's a definition. So a topological packing graph. So we say that this is a graph where the vertex set is a Hausdorff topological space, and where each finite clique is contained in an open clique. So, and just a definition of a clique. So a clique in a graph is a subset of the vertex set where any two distinct vertices are adjacent. So what does this condition mean? So it means that if you have some, say think of spherical caps that are adjacent, so that means geometrically that these spherical caps intersected their relative interiors, right? So if you perturb these spherical caps a little bit, then they will still overlap in their interiors, right? And that's exactly this claim or this condition that finite cliques are contained in open cliques. So if you have a clique, if you have such a situation that packing objects overlap in their interiors, then perturbing them a little bit, it should still be a clique. So we want every clique, which is a subset of the vertex set, to be contained in an open clique, right? And an open clique is a subset of the vertex set that is on the one hand a clique, and on the other hand is an open set in the topology of the vertex set. Now, and so what we wrote, every finite clique is contained in an open clique, but actually you can check that it suffices to check this condition for cliques of size 1 and 2. So if we would require this for all cliques, that's sort of a funny thing, which is equivalent to requiring this for all maximal cliques. And then that would really change the definition, but I don't think this is important for the graphs we actually care about, but I think it's a funny fact. So this isn't really restricting the graphs in any way, right? Because you can always just impose the discrete topology, and that turns any graph into a topological packing graph. But so the restriction we get is, for instance, if we require our graph to be compact. And then you can, for instance, prove that a compact topological packing graph always has finite independence number. And in this lecture, I want to show hierarchies that converge in finitely many steps to the independence number. So that's going to be really convenient, that the independence number is actually finite. so you could wonder why are we dealing with topology if we're going to consider topological spaces such as a sphere, or maybe you want to consider projector space or something. And there you always have sort of a natural metric. So why do we bother talking about topological packing graphs? So one reason for this is that there are also cases where there's no natural metric to work with. This happens, for instance, if you pack different objects. So for instance, if you want to pack two sizes of spherical caps on a sphere. You can, if you really want to, you can still construct a metric that agrees with the topology, but it's something really ugly, non-natural. So that's one reason you might want to work with this definition. And also it turns out that this is actually all that you need to make everything work. Okay, so and then I want to go to independent sets in these compact topological packing graphs. So here's a bit of notation. So we'll use I sub t for the set of all independent sets of cardinality at most t. And then, so we have a topology on the vertex set, and now we also want to have a topology on these sets of independent sets. So how do we do it? Well, there are many equivalent ways of doing this. We can, for instance, say that this set of all independent subsets up to cardinality t. So if we remove the empty set from this, then we can get a topology by, well, first considering the product topology of v to the t, and then using this quotient map to forget the order of the elements, and then use the quotient topology. And then you just add the empty set back as an isolated point. Yeah, and if you would have a metric on V, then this is actually the Hausdorff distance that you get this metric. So what does that mean? That means that two sets of points are close in this topology if for any point in one of these sets, there's a point in the other set nearby. So normally, if you just consider subsets, that means that sets of different cardinality can be close to each other. But actually, if we work with compact topological packing graphs, then this cannot happen. So for compact topological packing graph, so first of all, this set of subsets is going to be compact, but also these, so if you take the sets of cardinality exactly t, so we remove all sets of smaller cardinality, this is both open and closed. So these are all disconnected components. Okay, so this is just the setup. So, and now we want to build a hierarchy for this. And of course, we want to use what we did yesterday. We want to use this moment hierarchy specifically for the independent set problem. So let me go back to that for a second. So yesterday we finished with this, right? We had a moment hierarchy for the independent set problem in a finite graph. So what do we do here? We maximize over vectors y indexed by subsets up to a certain cardinality. And then in the objective, we sum all singletons. And here, 1 up to 1 through n, those are the labels of the vertices in our finite graph. We have a normalization condition. We have that the moment matrix of this vector has to be positive semidefinite. And our vector is 0 for all dependent sets, but for all sets that contain an edge. Yeah, and just to check real quickly that okay, let's verify. Of course, this follows from the general theory that this gives upper bound, because Laurent showed that this is actually the moment hierarchy for the 0-1 polynomial optimization problem. But we can also check this sort of directly very quickly, so that this indeed gives an upper bound. So how do we do that? So we take an independent set, and then we construct a feasible solution for this problem, right? Now this feasible solution y is defined by y sub r is 1 whenever r is a subset of S. And then we consider sets r up to cardinality 2t. So you can easily check that it satisfies the normalization condition, that it is indeed 0 whenever S is dependent. And you can check with a double sum argument that this moment matrix is really positive semidefinite. And then the objective is going to be the cardinality of S. So this all works out. Oh, here's by the way the double sum argument. So you construct a square and then this is non-negative. So what this also shows is that we can actually add constraints to this program. So this vector y we constructed obviously is entry-wise non-negative. And we can actually add those constraints to the program. And that can make the bounds better. So let's do that. Yeah, so I want to talk about convergence now. And for this I want to, so there's this proposition by Lindstrom and Wilth that says that the cone of positive semidefinite moment matrices is actually this cone. So it's the cone of chi, did I write what chi s is? Okay, it's the cone of chi s times chi s transposed for all subsets S of the vertex set. And this chi s is the characteristic vector of S. So it's defined just like this y r. So so chi s is a vector, and the entry at index r is 1 if r is a subset of S. Yeah, this is an older theorem from the 60s in combinatorial optimization. So I do explain what moment matrices are. Okay, so your moment matrices are matrices of the form mt1y, as we saw yesterday, where y is a vector indexed by all subsets now. So this is not truncated. Oh, so I can remove the t here even, right? The t is n here. So, and Laurent uses this to give a direct proof for convergence of this moment hierarchy for 0-1 polynomial optimization problems in the most n steps. So we don't need these asymptotic convergence results we saw yesterday and the day before, but actually you can give a direct proof that you get convergence. And now if you look at the moment hierarchy for the independent set problem, we see that it doesn't actually change anymore, as t is it gets bigger than the independence number, right? If you look here, we see that as soon as t reaches the independence number, since y of s is 0 for all s dependent, this vector is just going to be 0 for a subscript with a higher cardinality. So because we get convergence in n steps, but after the whenever t is greater than alpha of g, it doesn't change anymore. We must have convergence in alpha of g steps, right? So it's an exercise to use these results by Lindstrom and Wilth to give a direct proof that this moment hierarchy for the independent set problem converges. So that's a bit easier than what Laurent did. So you also have to work with the localizing matrices that you don't have to do here. So you can give a direct proof. And actually, I will show something similar to this exercise later in the lecture for infinite graphs, but the notation is going to be a little bit different there. Okay, so here's the moment hierarchy again. But now I have a prime here, and that's just because there's this extra constraint I talked about that y is entry-wise non-negative. And as we go to bounds for packing problems, that's actually going to be important that we add those constraints. So again, so for finite graphs, we optimize over entry-wise non-negative vectors y, indexed by subsets of the vertex set, which is now just a set of labels 1 to n of cardinality at most 2t, where y of s is 0 whenever s is dependent, right? And then we have the normalization condition and the moment matrix condition. So what will we do for infinite graphs? So we're going to use this set I sub t. So that's the set of independent sets in our graph up to cardinality 2t. It's a topological space. And we're going to consider Borel measures on this. So for infinite graphs, instead of optimizing over these vectors y, we're going to optimize over these measures lambda. Now, of course, you could have just adapted this pt prime immediately to infinite graphs by just considering vectors on this indexed by this infinite set. But the way you do that, it's sort of harder to derive a nice dual program. And when we're really going to compute bounds, you want to work with the dual. Here it really helps to work with measures here, so that in the dual we are going to get continuous functions, and then we can approximate those continuous functions by polynomial polynomials to do really concrete computations. So the normalization condition now becomes that if we evaluate lambda at the set containing the point, the empty set, then this has to be 1. So recall y sub 2t, it's a set, it's a topological space where each point is a set. And the objective becomes lambda evaluated at all singletons, the set containing all singletons. So, and now there's the question, so what about the positive semidefiniteness of the moment matrix? So how can we adapt this from this empty y being positive semidefinite to something involving lambda being something which has to do with positive definite? Yeah, and that's actually, so we don't really know how to do this for lambda directly. So instead we just first think about what does this condition actually mean in the dual. Then we generalize that to infinite graphs, and then we go back to this, this setting. So the first step is to say that, well, saying that the moment matrix of y is positive semidefinite is equivalent to saying that the trace inner product of m of the moment matrix of x is greater or equal 0 for all positive semidefinite matrices x. So this is really just saying that the cone of positive semidefinite matrices is self-dual, as Frank mentioned in his lectures also. So, and now, well, this MT, this is a linear operator, so it is an adjoint, and which means we can write this condition that the moment matrix of y is positive semidefinite as saying that the trace inner product of y with ATX must be non-negative for all positive semidefinite x. So AT here is the adjoint operator. And then you can just write out what is AT explicitly, right? And if you do that, and you also go to infinite graphs, then it becomes this operator. So it's an operator sending kernels on IT, so continuous functions that go from this product to R to functions on this I sub 2t. And it works like this. So if we apply AT to K and we evaluate at a set S in I to T, then we have to compute the following sum. So we sum over all J and J prime in IT, whose union is equal to S. Yeah, and then the constraint for finite graphs that the moment matrix is positive semidefinite, this becomes the constraint that if we integrate this kernel of this function ATK against our measure, we want something non-negative for all positive definite kernels. Okay, yeah, and then we get the following optimization problem. So here we maximize this objective I mentioned before, lambda evaluated at the set of all singletons, where lambda is a positive measure that corresponds to entry-wise non-negativity of y, where lambda, of the normalization condition, lambda at the empty set is 1. And then this positive definite condition, which sort of is a dual way of formulating this, right? And this is from a paper together with Frank van Atten. Yeah, for each t, we sort of already know that for each t we get an upper bound because it's really an adaptation of this this hierarchy. We already saw for finite graphs, but let's check that it's really true. So for each t we get an upper bound on the independence number. So if S is independent, then lambda is oh, actually, there's one. I should add one extra thing. So we shouldn't. It's almost true what is said here. So for chi s, instead, if we are at level t, we need to sum here over all r in S of cardinality at most to t, right? Because we want lambda to be a measure on I sub 2t. So lambda should, for t smaller than the stability number, lambda is not really chi s, but it is a small variation on that, right? Okay, so, and as I said, this generalizes the Lacerre moment hierarchy for the independent set problem. And now of course, we want convergence also, because what sort of one of the goals here is to show that any packing problem in a compactor graph, that we can solve it in principle. So we also want a convergence proof. And for this, we're going to adapt the proof by Laat. Yeah, so for this, we can use Mobius inversions. Actually, normally, so in the paper, we call this inclusion exclusion, but I think there are some number theorists in the audience, so I just took this title. So what's going on here? So we have the following lemma. So for each signed measure, lambda on this I to the 2t, there exists a unique signed measure sigma, such that lambda is this vector valued integral. So what does this notation mean? So lambda is a measure, chi sub s is a measure, right? Chi sub s is this measure here, the sum of Dirac measures. And sigma is also a measure. So what this notation means is that whenever we evaluate lambda at a continuous function f, that is going to be the integral, where the integrand is chi of s evaluated at f, which is just a number, right? Integrated against sigma. And the reason I put Mobius inversion here is that, so if you take, for your post set, instead of division, you take set inclusion, then this lambda is the upper Mobius inverse of sigma. Now, and just as for the Fourier transform, you have that positivity is preserved in some way under this transformation. So if lambda supports this sort of positive definiteness condition, then on the other side, sigma will be positive and vice versa. If sigma is positive, then lambda will set aside this positive definiteness condition. Now, this is sort of about it's Mobius inversion, but it's maybe with a twist, or maybe it's two twists. So one is, instead of functions, we consider measures, right? So you cannot really talk about what this measure is at a point, right? So, and let me maybe explain this a little bit more, where this Mobius inversion comes from. So think of, say lambda is atomic. So say lambda is just a function. So and then if you evaluate lambda at a point, then this is the integral over chi s evaluated at that point, which is a set, right? In our topological space, points are sets. And then this is going to be 1 for all sets that contain that set, right? So that's why I say this is, and that means that you get the contributions of sigma on all s that contain the point you're evaluating lambda at, right? So that's why I say upper Mobius inverse. But yeah, so as I said, it's a little bit different because we have measures instead of functions. So if you want to prove this, you really need to prove everything by evaluating against functions. And it's maybe also a little bit different because it's sort of truncated. We have this truncation going on with this set I sub t. Okay, so here's again the hierarchy, so just the same as on the previous slide. So if t equals the independence number of the graph, so the independence number alpha of g, then I sub t is just going to be equal to I sub 2t, right? There are no more independent sets. So, and that means that we can immediately apply this lemma. So now, by definition, lambda is supported on I sub 2t, but this is the same as I sub t, which means that lambda is supported on I sub t, and we can apply the lemma. But this shows that, well, if you also use the normalization condition, that lambda at the empty set is 1, that shows then that sigma is a probability measure. And that means that this optimization problem is really reduced to this optimization problem. So we optimize over all probability measures on the set of independent sets. And then we optimize this integral. So we integrate chi of s, or we evaluate chi of s at the singletons, integrated against the sigma of s. But this integrand is just the cardinality of s. So the best thing you can do here is make sure that sigma is supported on independent sets of cardinality alpha of g, and then you get the independence number. You cannot get something bigger than that. This also shows, so if I go back a few slides, so here it is Lindstrom-Wilf business. What this is really showing, if you work out this exercise, is that, so you have the semidefinite programming hierarchy. And so semidefinite programming is linear optimization of a spectrohedron, right? But what happens in the Lacerre hierarchy at the final step, at the end step, is that the spectrohedron actually becomes a polytope. So the spectrohedral cone becomes a polytope. Polytope cone in your feasible set becomes a polytope. And then the extreme points of these polytopes are actually correspond to independent sets. So that's. And then of course, if you go to infinite graphs, you can no longer be optimizing over something more complicated, right? Some infinite dimensional version of a spectrohedron. So you cannot really expect this to become a polytope in the final step. But sort of the next best thing is true, right? It becomes probability measures, which is sort of an infinite dimensional version of a polytope. So yeah, it's actually, in the end, it's very, very similar. Okay, so let's continue to the dual hierarchy. So as I said, yeah, we do the convergence proof in the primal hierarchy, in the hierarchy of relaxations. And I think if you want to do a convergence proof in this dual hierarchy, I have no idea how to do that, even for finite graphs. That's really difficult, I think. So for the convergence proof, you really want to work with the primal hierarchy, the hierarchy of relaxations. But doing computations with this hierarchy is tricky. So one, it might be sort of tricky to work with measures, but there's probably a way around that. But it's more tricky that if you have a feasible solution, you don't actually get an upper bound, right? You need the optimal solution. Or sorry, but yeah, you need the optimal solution to get yeah, to get an upper bound, right? So and that's why we want to dualize. So if you work in the dual by weak duality, yeah, these give upper bounds on the values here, on the optimal values here. So if we work in the dual, any feasible solution is going to give us a rigorous upper bound, right? And so the game here is to, so what are we doing here? In the primal, we were optimizing over measures, which means that in the dual, you're optimizing over continuous functions. But we're going to write something like a Fourier series, inverse Fourier series of this kernel K, and then we're going to truncate. And then we're going to optimize over these finitely many coefficients that are left. And that's going to give us feasible solutions of this thing. And yeah, for each truncation, you get provable upper bounds. So yeah, so for each t, weak duality shows this gives an upper bound on the corresponding problem in the moment hierarchy, and hence an upper bound on the independence number. And of course, then you could worry about if you just have weak duality, so then this convergence proof of the primal hierarchy wouldn't be so useful because you wouldn't know that this also converges to the independent set number. But actually, we can show that strong duality holds. So the optimal value of this dual problem is equal to the optimal value of the primal problem. So in principle, we can solve any compact problem up to any precision by solving these dual problems. Of course, I say in principle, because in practice, this is not so easy to do, but in principle, we can do that. And then there's one question remaining. So the strong duality proof actually also shows that the supremums I was talking about, those are all maximums, those are all attained. For these infimums, so this is actually, it seems like a technicality. Is this an infimum or is this a minimum? And also if you, and so that's one question that we don't know the answer to in general, even for spheres. And another question is if you truncate the inverse Fourier transform, can you really find a sharp bound, an exact bound by some finite truncation, or do you sometimes need an infinite Fourier series? And this is, of course, this sounds like a technical question perhaps, but this is, of course, really crucial. So for all experiments that we have done for compact graphs, it always seems to be the case that yes, the infimum is attained, and yes, it is attained for some finite truncation of your inverse Fourier series. So for some polynomial. But of course, for non-compact graphs, this is not at all true, right? So if you, I will show that the first level, t is 1, is going to be well, first of all, the low theta number, which is the Delsart bound, which is the linear programming bound for spherical codes. So, and the non-compact analog of that is the Konauki's bound, right? And there we know that polynomials can never give an optimal solution, because by complementary slackness tells you your functions need to have infinitely many roots, and polynomials cannot do that. So you need this construction by Vyazovska, for instance, in dimension 8, of something that is not a polynomial, right? To really build a sharp solution. So this is really, I think, a distinction between compact versus non-compact. But I have to say, for compact, it's all conjectural. There are no proofs. So for the sphere, we do not know that the infimum is attained and that finite truncations can do it. Okay, so yeah, as I said, so next lecture tomorrow, I want to show how to compute this thing, also for t greater than 1. But now I just want to relate it to something that was also mentioned in Henry's talk, right? The Delsart linear programming bound. So I want to show how this connects to that. So put it in the, put sort of the Delsart bound in this framework. So, and for that, I first want to go to the low-fast theta number. So this is a very important graph parameter in combinatorial optimization. And as Frank already mentioned, it upper bounds the independence number and it lower bounds the chromatic number of the complement graph. It also upper bounds the Shannon capacity of the graph. So I already mentioned that the independence number is NP hard. So the Shannon capacity is even a sort of a whole different level of hardness. So the independence number is NP hard, but at least for finite graphs, you can just compute it by brute force if you want to. For small graphs, you can just try all sets, right? So subsets of the vertices. So for the Shannon capacity, this is much harder even. This is, for instance, the 7th cycle. We don't know what the Shannon capacity is. And the low-fast theta number also gives an upper bound on this Shannon capacity, for instance, proving what the Shannon capacity is for the 5th cycle. And for finite graphs, this is and actually, so the reason I mentioned this is, so loafers originally introduced the theta number to bound the Shannon capacity of a graph. So if you get a chance, that is a really nice paper to read. It's called On the Shannon Capacity of a Graph. Yeah, so for finite graphs, this is a semidefinite program. Right, so for infinite graphs, we can write this semidefinite program, or this infinite dimensional semidefinite programming as follows. So we minimize A over all real numbers A, and over all positive definite kernels F on this vertex set times the vertex set. With these conditions. So fxx is at most a minus 1 for all the vertices, and fxy is at most minus 1 for all xy not adjacent and not identical. Yeah, actually, I'm not going to show it, but using the Schur complement. So, so for finite graphs, you can use the Schur complement to show that this is actually, I guess you can see it looks kind of similar to this. If you plug in a t is here, so if t is 1, these are all the singletons plus the empty set. And here we have all the vertices. So it's almost the same. The only difference is the empty set. But you can use the Schur complement to work around that. And that same proof can be adapted to this infinite graph setting. So also here you have this low theta number is the same as this hierarchy for t equals to 1. Oh yeah, and so one thing, there's a theta prime here. And that's actually, so that's the same prime we have in the moment hierarchy, where we say that y is anti-rational negative. And that is here also. So you have theta, and then you have theta prime, where you also have some anti-rational negativity. And here in this dual formulation, that corresponds to having inequalities here as opposed to equalities. Okay, so here again, it's the same theta prime number. And then as observed by Beshogne, Olivier, and Valentin, this theta prime number actually reduces to the Delsart band. So in the final few minutes, I want to show how that works. And then it's a little bit of harmonic analysis. And tomorrow I want to do much more harmonic analysis, where we're going to replace the t is 1 here when we get the Delsart band for t is 2, where we get better bounds. So yeah, and here so the first thing is a symmetrization trick, and this is a really important trick in optimization. So we may assume this kernel K to be ON invariant. So what does that mean? So that means that K of AX, AY is equal to K of XY for all rotation matrices A, or all orthogonal matrices A, and for all X and Y in the unit sphere. So why can we assume that? So so maybe it's obvious for you, but let me spell it out, because I think it's very important. So if AK is a feasible solution, so you have an A and a K that satisfies these inequality constraints, and K is positive semidefinite or positive definite, then also this AK bar is feasible, where K bar is obtained by symmetrizing K over this orthogonal group. So we integrate over the normalized higher measure on this orthogonal group. So why is that? So that is because the constraints here are invariant under this group. And that is a really common trick in optimization. So if you have an optimization problem where the constraints are invariant under some group, then you can, just by this averaging argument, you can restrict your optimization to points that are also invariant under that same group. And this is also one big reason why optimizers such as myself are interested in, for instance, representation theory and harmonic analysis to do these kind of things. Yeah, and also I think it's sort of maybe nice to observe that in this story, harmonic analysis is sort of a tool to be able to do the computations. And in Henry's talk, it's more like he derives the bounds from harmonic analysis. So here, I derive the bounds from sort of combinatorial optimization techniques, and then use harmonic analysis to go to something we can compute. So how do we continue? So now we have kernels K that are ON invariant and positive definite. And then Schoenberg's theorem says that this then is a series with non-negative coefficients, and with here Gegenbauer polynomials or ultra-spherical polynomials. But they're just some family of orthogonal polynomials depending on the dimension we are working in. And convergence here is uniform absolute, and that's actually quite special. So normally if you want to write down such a series, so in general you only get L2 convergence, right? If you write such a Fourier series. But due to the positivity, you can actually prove that you get uniform convergence here. And this proof really depends on two things. One, that we find really many orbits. So here, orthogonal group acting on the sphere, we have just one orbit, so that's good. And that you have this positivity. So those two ingredients allow you to prove that the series converges uniformly. If you lose one of the two ingredients, you lose uniform convergence. Yeah, this shows that the theta prime number reduces to this problem. So I just replaced this positive definite kernel by this series. And then, yeah, the rest is still the same. So that moved it to the top. And now what we can do is we can, you see that everything here depends only on the inner product between X and Y, which makes sense because we symmetrized under the orthogonal group. Yeah, as also the term came already up. This happens because the sphere is a two-point homogeneous space. I think in Henry's talk that term already came up. So we can replace this dot product by U. And then we get this optimization problem. So, and if you know the del Sart linear programming bound, this is basically it, right? So you remove A, and maybe the different ways of formulating it, but then you get the del Sart linear programming bound. And then if you truncate this infinite series, then this is a polynomial, and then this is a linear program, except for you still have infinitely many inequality constraints. And that is sort of, now we get to see what I mentioned right in the beginning. We started with a sum of squares hierarchy. Then we went to the dual of that, the moment hierarchy. Then we generalized this moment hierarchy for the independent set problem to infinite graphs. Then we looked at the first step in that hierarchy and sort of used symmetry to reduce it to this del Sart band. And now we see that it's almost a linear program, except with sort of a semi-infinite linear program. So it's a linear program, except that we have these infinitely many inequality constraints. And for that, actually, we can use a sums of square hierarchy again to model that as a semi-definite program. So I'll say more about that also tomorrow. So that's it for today. Thank you for your attention.